El Nino's been good to Ottawa, it hasn't been good here. We had probably the first green Christmas I ever remember. So I'm the first of the people to repeat. So you get the second, get to hear me a second time. So I'm going to start by reviewing a bit about what I talked about last time. Like last time, please interrupt me anytime you want with questions. I'll try to keep everything so that you can follow it. I hope you can. And, well, let's see how it goes. So let me start out with the way I didn't start out before and say that what I'm talking about and the ideas are not only my own, but I represent a large group of people in Ottawa in the Joint Laboratory for Attosecond Science. I showed you the two labs. I told you one was modeled on Buckingham Palace. And so I worked in the Palace, and here we are standing in front of the Ottawa version of Buckingham Palace and the group with most people in it. It's about 30 people all told, students, postdocs, and staff. Now, first thing I said last time, I think the very first few were, I just want to reinforce it again. A short pulse is just an interference in time. It's no different than the interferences you know in space. It's just an interference in time. And for an interference in time to work well, all the frequency content of the pulse, shown here as 7, have to be phased perfectly so that each peak adds perfectly at the time it's going to add. So it's essential to be able to organize a broad bandwidth of radiation to be perfectly phased. Now you've heard many lectures since my first lecture where I introduced or when I told you this, and probably you've thought about it as you listened to Margaret just earlier, and as you listened to others, and you've seen how it's done in the Attosecond science. But I wanted to go back to that to start out, just to make sure you remember it. Now, other things to remember. I said that to make a short pulse, we need a nonlinear process in order to legislate that all of these frequencies are phased together. If there's not a nonlinear process, each frequency evolves independently of the other. They don't speak to each other, and so there's no way to get them put phased together. So we need a nonlinear process, and I showed you what that nonlinear process was for lasers. It was really a chi-3 process, Kerr-Lenz mode locking, or a Kerr effect, a chi-3 process. And I showed you how this begins to arise in attoseconds. And you heard more from other people, including Margaret this morning. I also talked about how it's important to measure. So to measure something, to measure a short pulse, we have to know how they're all phased together. We can't just measure independently frequencies. If we measure independently frequencies, all we know is the bandwidth. So we have to be able to link those, and that requires a nonlinear process. And in the last lecture, I talked about how these nonlinear processes can be used in autocorrelation and in frog. I introduced both of these ideas. I didn't tell you how we make these kind of measurements in attoseconds, and nobody has brought it up yet, at least directly, so I'm going to talk about it next. Or not next, but very close to next. Okay? And then finally, I talked about how we make fast measurements, and largely that's pump and probe, and that is intrinsically nonlinear. So nonlinearity is deeply built into everything here. And in conventional femtosecond lasers, this is all chi-3 or low order nonlinearity, and in attosecond, it's a lot, not the only, but it's a mixture of both. I showed you this figure, and I said that all of the work done really up to around here in the mid-1990s was all based on chi-3 nonlinearities, learning to control these and use them well and integrate them with lasers, and of course dispersion control, which is not shown on this. And the work that's led to the advances afterwards is all coming from this very high order or extreme nonlinear optics, and that you've heard many people's perspective on as you've heard talks over the last little bit. And I introduced some of the ideas of this extreme nonlinear optics in a very qualitative way, and I gave you an assignment. I don't know if anybody did it, I gave you a couple of assignments. I said start to work out some of the trajectories involved in this problem, and we spent some time talking about those trajectories. We said that an electron that ionizes in a time-dependent field, for example, there's just one cycle, and if it ionizes it relatively late in the phase of the cycle after the peak of the field, if you do F equals ma, which some of you might have done, it comes back and collides with low energy relatively early, giving out a burst of radiation as it gives out its energy to a photon by recombining to the ground state. Or alternatively, as it induces a dipole, and the dipole oscillates because of the interference of these two. These are just two alternative perspectives on the same process. An electron born earlier will come back later, giving you higher frequency radiation. These numbers are arbitrary here. You heard from Margaret's talk that it can go to a kilovolt. And a number that's born at the optimum time, just 17-degree phase after the peak. The number that's born in the optimum time comes back and collides at the zero crossing of the field, or very near it, and it has the maximum energy in the problem, and you've seen this number come up periodically, 3.17 UP plus IQ. That's the maximum number, and Margaret just spoke to you about how you can increase that maximum number and push it out. And we also talked about the possibility of other trajectories coming later, and there is two possible energies from each trajectory, but in a real phase match situation, in a real laboratory, they have a different divergence, and you can set up an experiment so that these later, longer trajectories, or later returning ones, can diverge, and you don't have to look at them very much. So largely we can concentrate on these. And these are the recollision electrons give the radiation. This is the nonlinearity. This whole process is converting infrared photons to very high energy photons, so it's really nonlinear. It's just a funny way to look at the nonlinearity. We don't even think in photons mostly. Only here and there do you think in photons. Mostly you don't. It's just a different way to do it. And I also gave you this quantum perspective on it. I said that what I said classically could be transferred into a quantum mechanical way of looking at it. The quantum mechanical doesn't have a real particle, of course, that really ionizes. It has a wave function, the ground state often of the atom, but it could be whatever is the ionizing this, state of the atom or molecule or solid in fact. The electron tunnels or ionizes in some way. It has to get free. Tunneling is the most beautiful way to think of it getting free. Out comes the electron by tunneling. Tunneling creates a more or less continuous wave function. Actually, you heard about how you calculate that in the talks by Lars Manson yesterday. And he actually talked about how you find out what happens out here in the continuum and what happens inside, and you match the wave functions. So it's the beam splitter. That's what he really described. He just didn't use the word beam splitter. It's a beam splitter for the wave function creating a wave packet plus the wave function. Two parts of the same wave function. The wave packet moves with this classical-like motion. Each moment of birth, each trajectory is a portion of this wave function. And I said that you would even think about working out these classical trajectories and the classical action of the electron along these trajectories. And the sum of these trajectories is that wave packet. The final step, the electron recolliding, is the interference between the two components of the wave packet. And I said, I ended up, I think that's the only thing I'll do with the review. Maybe I have one more. I ended up with this image, which tries to make very qualitative, so you can feel in your fingers why the harmonics are emitted, why they have a clear phase, why they work so well. So here you see what was an initial wave function, that was Gaussian in this image. So you know what a Gaussian looks like. Here you see an image of a recollision white electron coming back from the left to right. I got to make sure I get it from your side. Coming back from the left and the right, it's shown as a plane wave coming in. Of course, it's coming in like this. And here is the sum of these two, because the wave function is the sum of the two components of the wave function, the original one plus the wave packet in the continuum. But of course, the probability of finding the electron is given by the wave function squared, so here's the square. When you square it, these bumps that stick up in the wave function are more prominent because of the squaring. So this is just the squaring of that. And then this is the dipole. This is just projecting it onto the dipole. Where's the charge? Is it to one side or the other? Here's the dipole, and that's the dipole at this moment, or this overlap between the wave function and the wave packet, or wave function and the wave packet. But the wave packet is moving very rapidly, and so very rapidly, this is the interference pattern. Now you know how to look at it. The dipole has moved to the other side, and as this wave packet propagates through the wave function, there's an oscillating dipole, the oscillating dipole emits radiation. In fact, if you were to look at the wave packet coming back, that's the F equals ma calculation, you would find that the frequency of this, the frequency, which is the momentum, is increasing with time, and that's the chirp that I showed you from a classical perspective earlier. So you can see everything here. And you can see why the amplitude and the phase of the emission is so coherent and so beautiful at the single atom level. And in the multiple atom level you just heard about in the last talk again. You heard about from Ken Schaefer yesterday. You can represent that dipole here. You might want to just look at it for a moment. The dipole is given by the wave function times the recolliding times r times the wave packet coming back. If we think of it as a plane wave, it's got some amplitude at momentum k. It's got a e to the I kx, e to the omega t. And to a large extent, our measurement of the harmonics, which is measuring the dipole acceleration, of course, which we're looking at with the harmonics, is really a measurement of this process in which we know omega, because we're measuring omega. Maybe we can assume omega relates to k, so in some ways we know k. And so in some ways our emission is a measurement of this, where the unknown might be the wave function. I just put that in as a teaser for you, because I'm going to come back to that tomorrow, and maybe I'll even come back to it at the end of the day. Then I finished up, I guess I remember this, I finished up with measurement, and I'm only going to show you autocore, just to remind you of how measurement is done with visible pulses, not with Attosecond. With visible and near visible pulses, the pulse that you wish to measure is being brought in to a beam splitter of some sort. Let's assume it's a perfect beam splitter, so what comes out this way and what comes out this way are perfect replicas. If they aren't, we would set it up so that they were. So they went through the same amount of material. So you can make it so they're perfect replicas. One beam goes through a delay line, another beam comes through, avoids the delay line. And so now by moving the length of the delay line, we can move the relative timing between one replica and the other. And now overall, we find a way to make the pulse measure itself. Make one replica measure the other replica. Here is shown autocorrelation, which is the simplest and maybe not the best of the methods for measuring the duration of pulses. In autocorrelation, you can imagine a pulse comes into a second harmonic crystal. It will possibly make its own second harmonic, but it will go off in the direction of the laser radiation from momentum conservation. The other pulse will come in its other direction, creating perhaps its own second harmonic going off in another direction. But if the two pulses are simultaneously overlapped in the crystal and it's appropriately phase matched, it's possible that you take one photon from one pulse and one photon from another, creating a second harmonic consisting of one and the other beam. Of course, it goes to the bisecting angle from conservation of momentum. It goes to the bisecting angle, and we can look at that and measure the degree of overlap between the two pulses. And that's what's measured in correlation. I showed you the functional form of it, and I said, work out what the width is for a Gaussian pulse. I'm not sure if you did or not, but if I gave you a different shape, you would get a different width, and that's the trouble with it. It's good, but it's not perfect. It's okay. And I talked about other techniques, but I won't go into them. So now I want to go into something new, and this was only the review, just to remind you of what I said last time. And some of them were reinforced by others, although I took a much more laser perspective in my first talk, because I wanted to give you the background. So now I want to go to measuring attosecond pulses. How do we measure an attosecond pulse? If you go back to this, it looks kind of discouraging. You can say, I'd like to do the same thing, but where are you ever going to get a beam splitter for an attosecond pulse? It's got a huge bandwidth, as you know. So what could possibly be a beam splitter? It seems hopeless. I think it is hopeless. It seems hopeless anyway. And while you bring the beams around, let's imagine it wasn't hopeless and you could find a way to do all of this. What are you ever going to get for your nonlinear medium for an attosecond pulse? We heard Linda Young talk about how X-rays don't do much nonlinear at all yesterday. So we're not going to very easily find a nonlinear medium here, at least. We'd have to look hard. And one we understood would even be harder, I'm sure. So it seems hopeless. So what we do is the standard way, the gold standard, I said, is the attosecond street camera. So the attosecond street camera is rather a simple idea. In some ways, it's a retro idea. It's what we did in laser physics, almost in the first days of lasers, when we didn't know better ways. And the idea was you bring the laser beam in to be measured, you photoionize something with it. In the early days of lasers, you came into a photocathode and made electrons in a photocathode and sort of hoped that these electrons were a replica of the pulse that came in. And then you tried to measure this replica pulse in a street camera. I'll show you an image of what the street camera looks like in just a moment. But, well, photocathodes are a problem, but maybe they're not a problem because atoms could be a reasonable photocathode. If you think about something like a hydrogen atom, let's say, a hydrogen atom, when you photoionize an electron by the electron, you create a replica electron wave packet in the continuum of the pulse you came in with. In fact, it's almost the inverse of what I just said before about making the attosecond pulse. So photoionization creates a replica photoelectron to the pulse that you wish to measure. It's a replica in amplitude, although it's interpreted through the transition moment, but for simple systems we would understand it. It's interpreted through the transition moment, and it's a replica in phase, again interpreted through the transition moment. So as long as you don't have a transition moment, the photoelectron wave packet that you create is a replica of the attosecond pulse that you brought in, or the pulse, doesn't have to be an attosecond pulse. And so the trick is to try to measure this photoelectron replica instead of the attosecond pulse itself. Okay? Just to make sure it's clear, here's an image. I took it from an image from Terence Krauss of how a street camera works, and I'll just tell you where the changes are. You would have brought a pulse in to be measured to a photocathode. We're going to replace the photocathode with just a gas of atoms. But that doesn't make much difference. We make photoelectrons. In the street camera case, we would have got those photoelectrons and pulled them as fast as we could away so they don't diffuse and so they don't get all mixed up, right? Because they disperse like mad. We would have pulled them as fast as we could in between deflection plates, and then the first electrons would see a rising voltage and get deflected more and more and more and more the later and later they came in, or depending on which way the field is going. And you could see in space a replica of what you had in time out here if you did it well. But how fast can you turn on the voltage in the deflection plates? Not so fast. And how it's tough to get these electrons in, especially if they're attosecond electrons with the huge spectrum, with them not dispersing and becoming and losing your information. So instead of doing that, we say, let's take an atomic gas, let's put it right between the deflection plates, but let's get rid of the deflection plates, so I don't even mean put it. Let's use a laser beam, which is a time-dependent electric field. So just something like a sweeping field that you put in the deflection plates can be placed by a laser beam itself. So use a laser beam instead of the deflection plates. Put the atoms right there in the middle of the laser beam, create the electrons so that they immediately see the field. And then, well, so replace the photocathode with atoms. I'm going through these, I should go back. Replace the time-varying electric field with an infrared laser beam. The beam you use to create the attosecond pulses are just fine and is used by almost everybody. And measure the energy of the electrons instead of the displacement, but it's the same idea, right? You know, measure the lateral energy instead of the displacement. So that's the idea of the attosecond street camera. It's a conventional street camera concept moved into the attosecond, and it works very well. Just make sure that you understand now how it works, and I'll take two images, just simple images, to reinforce this before I go through. An atom photoionizes, creating a photoelectron replica. These electrons from photoionization can be going in any direction they wish, consistent with the transition moment that created them. So I will assume that they're going in any direction, but of course this could be modulated by a directional component of the transition moment. I'll represent them by their velocity. Their velocity is given by the photon energy minus IP. In this case, it's a range of photon energies minus IP. So you might say I should represent this by a wide distribution, but that gets kind of awkward. I'll show you the experimental results and you'll see the wide distribution in a minute. Okay? So now, this is the initial photoelectron distribution that you've made, represented this way. Now let's do the same thing, but create the electrons in the presence of an infrared field. We might create it when the infrared field is peaked. If we do that, and you follow F equals MA, just integrate it like I asked you to do yesterday, you will find that the photoelectron distribution is unaffected if it's created right at the peak of the field, and so I represent it there by the same circle we had before, one without. That is, if you integrate out to the end of the pulse, for a pulse that integrates to zero, from the peak of the field, it will come back to where the same velocity that it was created with. However, if you create the photoelectrons at different phases, let's say at the zero crossing, they're moved off to the left or off to the right, depending on which way the field was pushing these photoelectrons, and then you integrate to the rest of the pulse. Okay? So I just happen to know, I don't integrate to the rest of the pulse, I know when it's made at the peak of the field. But if you want to prove it to yourself, take some short pulse, make sure the field integrates to zero, so it's a realistic short pulse, one that can be radiated, created at the peak of the field, integrate out to the end, and you'll find out what I said. So it can be an assignment again. I didn't make it up as an assignment. I have something different at the end of this. So you can calculate what happens to the velocity of these electrons, and as you can see from the image, it depends in the direction you look. So we're going to want to look at some particular direction, and we're going to watch what happens as we create and put an attosecond pulse. Now let's imagine the attosecond pulse itself. It has some duration, so some part will be created here, some part can be created there, not only at the peak of the field. So this distribution, which is shown in black, will be spread out a bit. On the other hand, if I got the phase differently, it'll be moved out here and it'll be moved around depending on this range of times that the electron is released and its integration to the end. And so this gives us, well, I think the next view graph is an image. This gives us 2D information. So here is a setup. A beam is brought in, taken in to create an isolated attosecond pulse in the jet. We select off a piece of the beam, bring it over to drive the street camera. So we just bring it around, stabilize it to make sure it's stable. And then we bring the beam to be measured, focus it into a second jet. This could be our hydrogen jet. It's not hydrogen. In our case, it's helium. But hydrogen's hard to deal with. But in principle, it could be a hydrogen jet. And here you create the photoelectrons. You look in one direction, you catch these photoelectrons, and you measure their spectrum here, as a function of time delay. So you see the oscillation up and down, up and down, up and down of the distribution. You see a brightening and darkening of the distribution. And this has all to do with how this distribution of photoelectrons released in energy and time are created. So as I said, you can go back with F equals ma, and you can calculate almost everything here. I have a view graph, but I didn't put it here, where I have a comparison of a calculation made based with F equals ma, and a calculation done with the strong field approximation quantum mechanically. And you can almost not tell the difference. So this now gives us information. Actually, since you remember what I said about frog, and I said about autocorrelation, let me go back and remind you. Autocorrelation gives you one number, the energy of the second harmonic pulse, as a function of delay between the two pulses, one and its replica. And then I said, but there's a theorem that says that it's impossible to reconstruct uniquely the pulse duration from 1D information. You really need 2D information to reconstruct the pulse duration. And frog was a generalization of autocorrelation to look at the spectrum. So here, we equally have a two-dimensional information. We have energy and delay. It's like spectrum and delay, so we have almost frog-like information. In fact, we can do a frog reconstruction or something very similar. Okay, so that's the idea of attosecond measurement. I'm going to show you an attosecond pulse, and I'll come back to attosecond measurement because I'll show you it applied in a minute. But I wanted the concept to be clear. So, anybody with questions? Yes, please.
Is the assumption here that the attosecond pulse is weak compared to the infrared pulse? So you can do F equals ma with the only infrared pulse?
I think that, yeah, basically, I suppose it is in a sense. They always are weak in a sense. You're struggling always for photons because cross-sections are relatively small and beams, yeah, I guess it is. It probably would be hard to get a realistic case where it would not be. Yeah, I'm sure it is. It's so much so I didn't think about it very carefully before. That's why I'm stopping and hesitating a bit. Yes, I think.
Which pulse does the photoionizing? Is it the TISAF or the...
Oh, no. It's the attosecond pulse that's photoionizing. The TISAF has to be there only to accelerate the electrons, but not photoionize or not photoionize in any way that you cannot distinguish. If it does photoionization, you want its the electron's energy to be out there, distinguishable clearly from the ones I release, the photoelectrons I release in a question. So the attosecond pulse is making a photoelectron replica, and that replica is being measured by this frog, by this gate, which is the infrared pulse that's manipulating these photoelectrons to put it in frog-like wave. So the measurements seem to be extremely accurate. There really is no obvious limit to how short a pulse you can measure. Although it's photoelectron spectroscopy is always hard. You're always measuring only 1 or 2 or 3 or 4 electrons at once, and so they're always difficult to do. And cross sections of said are weak, and photon attosecond pulses, although great, could be stronger. So there are limits in practice, but in principle, I think this has solved the measurement technique. There are other ways, but I will not introduce them in this course. Any other questions? Yes, please.
What's the unit of the delay?
Excuse me?
The unit.
I still didn't understand.
The unit.
Oh, the units here. Sorry, I'll give you real units in a minute, but this is being modulated by the infrared laser, so 800 nanometers in this case. So I'll give you one with real units. This is just an illustration right now. So this is an 800 nanometer periodicity, and so you're pushing it this way, pushing it this way. So it's one period of the 800 nanometer light. And this depends on this is the spectrum of the pulse as seen through photoionization. So in other words, I've got IP of energy in the